Hi everyone. Today I want to talk about how we can use numbers to represent groups of objects in real life. We'll start with a short activity that's going to get us introduced to our topic, and then we're going to dive a little bit deeper in and we'll work together through a problem that's a little bit more complicated. Alright, let's get started on that first activity that I was talking about. In a second, I'm going to quickly show you some dots on the screen. They're only going to be up for a few seconds, so I'd like you to try to remember what they look like without counting them. Here they are. All right, now they're gone. Let's discuss a few ways that we could describe that group of dots without just saying the quantity. So first, we have 2 rows of 3 dots with 1 dot by itself. Next, we have 2 columns of 2 dots and 1 column of 3 dots. And last, I have a 3 by 3 square that's missing 2 dots. These are just a few examples of ways that you could describe them. If you want, you could pause the video now and think of a few ways that we haven't discussed as a little bit of a challenge for yourself. Okay, on their own, right, these descriptions aren't that useful to us in a math context. But what if there was a way that we could use numbers to represent these descriptions so that they become more useful to us as mathematicians? It turns out that there is, and it's called an expression. An expression is a group of numbers and operators. Operators are your plus signs, your minus signs, etc., that are describing math operations like multiplication, division, subtraction, addition. And so an expression is a group of numbers and operators that represent a value or what something is worth. Then when we add an equal sign and the value of the expression on the right, then we'll get what we call an equation. And you'll see here at the bottom of the page a little diagram that's labeled with each of the parts of an expression. So for us as mathematicians, expressions and equations are really useful for when we want to use math to solve real-life problems. We can use them to describe a number that we've come up with from a real-life problem. So let's go back to our examples from the dot problem and come up with some expressions to represent each of our descriptions. For the first one, we'll write 2 times 3 plus 1 because we've got 2 rows of 3 dots plus 1 dot on its own. For the next one, we will write it as 2 times 2 plus 3 because we've got 2 columns of 2 dots plus 1 column of 3 dots. The last one we'll write as 3 times 3 minus 2 because we've got a square that's 3 by 3 dots that's missing 2. If you'd like, here you can pause and think of expressions for the examples that you came up with for yourself last time. If not, we'll just move on. When we look at all of our expressions side by side, you'll see that each of them come out to 7. That's because there were 7 dots in that picture that I showed at the beginning. And you'll see that the number 7 can be represented lots of different ways, and this is true for pretty much every other number. And we're going to use this fact to help us solve this problem up next. So now that we've gotten warmed up with our topic a little bit, let's try out a problem that's a little bit more complicated. Here's the problem. You are holding a big event and you want to play a few different games which require different sized teams. Some games need a judge, so for those games there will need to be one person left out. How many people should you invite if you want everyone to participate in each game? For the first game, when everyone's put into teams of 2, there's always one person left out to be the judge. For the second game, when everyone is put into teams of 3, there's always one person left out to be the judge. For the third game, when everyone's put into teams of 5, there's one person left out to be the judge. And for the fourth game, when everyone's put into teams of 6, there's always one person left out to be the judge. And the last game doesn't have a judge, but we have teams of 7. So when everyone's put in teams of 7, there's nobody left out. If you want to challenge yourself, you can pause the video here and try solving the problem on your own, but I'm going to work through it step by step with you. We'll use a hundreds chart right here to help us keep track of the answers that we're considering. So it turns out that there's 2 of our rules that give us a pretty quick and easy way to eliminate a lot of possible answers. First, let's look at the last rule that I was just talking about. When everyone's put into groups of 7, there is nobody left out. This is just another way of saying a multiple of 7. So, we can eliminate every number that isn't a multiple of 7. I already went ahead and crossed them out here. Next, let's look at the first rule. When everyone is put into groups of 2, there is always one person left out. This is just another way of describing an odd number. So we can eliminate every even number. I've already gotten rid of all the numbers that we eliminated in the last step. So here we can just go through and cross out all of the even ones. Remember that even numbers end in 2, 4, 6, 8, or 0. Now we just have a few numbers to check, and we have 3 rules left. So let's look at the second rule, which we skipped before. When everyone is put into groups of 3, there's always one person left out. For this rule, you can just go through and divide each number by 3, keep track of the remainders, and eliminate each number that doesn't have a remainder of 1. I've already done that here and eliminated each number that doesn't match our rule. Let's skip the next rule for a second and think about the fourth rule. When everyone is put into groups of 6, there is always one person left out. Just like last time, try dividing each number by 6, keep track of the remainders, and eliminate each number that does not have a remainder of 1. You'll see something a little bit interesting. We actually end up eliminating the exact same numbers as last step. Could you think of a reason that might explain this? Back to our problem. We've eliminated the same exact numbers in the last 2 steps. We only have one rule left to check. When everyone is put into groups of 5, there is always one person left out. So, just like last time, divide each number by 5, keep track of the remainders, and cross out any number that doesn't have a remainder of 1. That leaves us with only one number, 91. So we should invite 91 people to our event. Again, if you want to challenge yourself, you can think back to the expressions that we wrote for each way we describe that group of dots and try to write an expression that represents each one of the rules from our problem, now that we know that the value of each expression should come out to 91. As you can see, expressions are a really useful tool that we can use to turn words from a real-life problem into numbers that help us represent our situation in mathematical terms. In the future, you'll probably use expressions a lot to solve word problems in your math classes, and this is just the first step.